I did my master's and PhD actually in the United States. I'm from the United States, but I work in Japan. I am an assistant professor at the Kyushu Institute of Technology in Kitakyushu, Japan, and I work in space engineering, in particular on satellite projects, nano-satellite projects, small-scale satellites. I'll talk about those today. And in Japan, especially at this institution, we're very interested in working with space agencies throughout the world, especially in emerging space markets. So we've been communicating with the Mexican Space Agency and, by association, Mexican universities. So I'm here to talk about the following. A brief introduction to my university where I teach, and then I'll talk about our laboratory, Le Seine. I'll spell out that acronym later. It's a river in France, actually. Yes, yes. And I'll talk about our space research themes and our satellite testing facilities that are available to industry, to other universities, and to international partners throughout the world. Then I'll talk about our satellite projects, and finally how students or staff members at agency or some industry could get involved with our university. Finally, a conclusion to go over the main points. And I should say that the opportunities are not just for academia or space agencies. At the professional level or at the industrial level, we also have opportunities to work together with our university, especially for satellite testing. Just a little bit more about me. I did a PhD in astronautical engineering, and in particular, I studied electric propulsion. I studied gridded ion thrusters, so very high efficiency, low mass thrusters. They've been used in space on a few missions. One Japanese mission to an asteroid called Hayabusa. They retrieved some asteroid material, returned it to the Earth, and NASA did something called Deep Space One, where they used an N-star thruster, a gridded ion thruster, to send a satellite into deep space. And secondly, I studied lunar science as part of my PhD. I studied and am studying how the solar wind interacts with the lunar surface. The moon has no magnetosphere. The core of the moon cooled and stopped rotating about 4.2 billion years ago. So the solar wind, the charged particles from the sun, strike the surface directly, unlike Earth, or Earth is protected by the magnetosphere. So anyway, that's my background. And I'll just go into the presentation. If there are questions at any point, please stop me and ask them. And of course, there will be opportunities for questions at the end. So QTech, or KIT, the acronyms are interchangeable. It was founded in 1909 as a private university. And so it's over 100 years old. And we have about 4,400 undergraduates and about 1,700 graduate students. So it's a fairly small university. It's science and technology only. But we do have almost 400 academic staff members, professors, associate professors, assistant professors, and postdocs. So the ratio of students to academic staff members is about 13 to 1, which is very good. And actually, Kitakyushu is very strategically located. It's located here in southwest Japan. And because of its location with respect to China, and because of natural coal, in the late 1800s and early 1900s, it was a very wealthy steel city. It still is. And the university, QTech, was formed as a private university by wealthy steel barons in 1909. Eventually, it became public. But that's where the university is located. About 1,000 kilometers, this is cut off a little bit, but Tokyo is here on Honshu Island, and we're about 1,000 kilometers west and a little bit south. The population is about 1 million, so about 23 times smaller than Mexico City. But the cost of living is fairly low. So for students, that's important. And here are a few pictures of the city. These can all be found on Google. Sushi market, one of the bridges, some festivals in Japan, and one of the popular malls. We have 3 campuses. Tobata is the main campus. It's the engineering campus. That's where I work. We also have a life science campus in Wakamatsu. It's a region of Kitakyushu, and a computer science campus in Izuka, about 30 kilometers to the south. So they're quite centrally located. Very briefly about each campus. This is the campus where I work, and I belong to the systems engineering department, as does the professor that I'm under, Professor Mengwu Cho. Some of you may have heard of him. He actually was at the ISU teaching a little bit in the 1990s, but he's a Japanese professor who founded this lab. And we work closely with the electrical and electronic engineering department as well. The other two campuses have the following departments: computer science and some artificial intelligence. And at the life science campus, the focus is mainly on biological functioning and brain science. These two campuses I don't know much about, so I'll try to answer questions if they come up. Earlier I mentioned that we are trying very hard to work with international institutions. This slide summarizes that. As of September of this year, we had 84 official partnerships with 23 different countries and regions, mostly China, due to the strategic location. But we are expanding into Southeast Asia, Europe, and more recently Africa and South and Central America. You won't see Mexico on this list, so hopefully that will be remedied in 4 or 5 months. We're working hard with the agency to set something up. And in terms of foreign students, we're mostly domestic, mostly Japanese students, so about 6,000 students. As of May 1st, only 238 of those were international. But this number is growing, especially in space engineering. I'll talk about that more later. Most of our foreign students are Chinese or from Southeast Asia, but we do have students from many parts of the world. So that was very brief. There's lots of information about the university that can be found online. If you'd like, I'll provide you with the link, the English link for the Japanese university webpage. Next, our laboratory. This is where I teach, in the Laboratory of Spacecraft Environment Interaction Engineering, or the SEEM. And we were inaugurated in December of 2004. My professor, or I should say the professor that I work with, Mengwu Cho, he started at QTech in the late 1990s, and about 6 years later, he formed this laboratory. We have 11 academic staff. I'm one of the assistant professors. Our annual research budget is fairly small, about $1 million US. It fluctuates a lot. Some years it's 2 or 3 million, some years it's less than 1 million. So that's just an approximate average. As I mentioned, space engineering education started earlier than 2004, actually in 1993. But this was at the undergraduate level, and that program still exists. It's for bachelor students. That class size is a little bit larger, about 30 students per class. At the graduate level, it's much smaller. The class I'm teaching has actually 18 students, I think, so that's one of the larger ones. But it's a class for both foreign students and Japanese students. Then in 2004, this lab was established, and in 2010, we established a Center for Nanosatellite Testing. And that's very crucial for industry and for agencies who are developing small satellites. I'll talk about that more briefly. Our research areas. So I'll talk about research then satellites. These are the 4 main research themes of our laboratory. These are fairly traditional space applications. This is the biggest area, electrostatic discharge. Now this is difficult to see, and what it actually is, this is a solar array surface. This was imaged with a black and white camera, but this is an arc discharge taking place on a solar array surface. In space, plasma is the dominant species. The pressure is too low for plasma to recombine. For example, in this room, if we tried to generate a plasma, the pressure would cause the ions and electrons to combine very rapidly. But in space, due to the low pressure, there's charge separation. What that means for solar arrays or other charged objects is that there can be arcing. If the potential between any 2 points on a surface is large with respect to the pressure and the plasma, there will be an arc and an electrostatic discharge. This can lead to satellite failure, and it has in many cases. So the primary objective here is to understand when arcs occur and how to mitigate them. We're also looking at material degradation. Polymers in particular and dielectrics are very susceptible to radiation damage. So we're studying from a UV and ultraviolet perspective and an high electron energy perspective, how materials degrade in space. We're looking at hypervelocity impacts. Recently, space, especially low Earth orbit, about 300 to 800 kilometers from Earth's surface, has become very cluttered with space objects and debris. So we're looking at hypervelocity impacts. And fourth, this is fairly new, nanosatellite environment testing. So not just the effects of plasma on the satellite, but the effects of acoustic shocks and vibration from the launch, radiation effects from charged particles from the sun and other radiation, and outgassing, many environmental effects that kill nanosatellites. The failure rate, the initial failure rate, the death rate of nanosatellites is about 50%. It's very high, and there are quite a few reasons for that, but we're focusing on reducing that percentage. And we work with agencies, industries, both locally and internationally. So very briefly about our ESD facilities, we have 3 primary chambers, and they simulate different plasma environments: the geostationary plasma environment, the polar Earth orbit environment, and the low Earth orbit environment. And our facilities are one of 3 in the world that have this capability. And because of that, and because we have such heritage in this field dating back to the early 1990s, we've tested satellites from an ESD perspective. This is testing the solar cells in a plasma environment. We've tested satellites from all over the world for almost 2 decades. And this is something that we still do. We also recently have begun to conduct experiments in space. So we started out as a ground-based experimental test facility, certifying solar panels and satellites before they were launched into orbit. Recently, we started doing these experiments. We've done 2 at the International Space Station. There's a lot of text on this slide. So what we did, we put a solar array, novel technology solar array on the International Space Station and tried to understand why and how it was arcing. Normally, we need a dedicated satellite mission to do that, but in this case, we just put it on the outside of the ISS. Also, very recently, 2013, we attached a charging sensor to the HTV module. The HTV is Japan's cargo module to send supplies to the International Space Station. And there was concern that due to the plasma in low Earth orbit, the potential of the module as it approached the space station was very different with respect to the plasma potential. The reference potential in space is the plasma potential. The ISS is fixed to about plus or minus 160 volts with respect to this potential. It has active devices to mitigate charging, but this vehicle does not. And previously, we weren't sure what the potential was. So we put a charging sensor here, and we confirmed that there was no problem. But it made the Japanese government feel a lot better. I mentioned hypervelocity impacts. We have a test facility. We use a 2-stage light gas gun to accelerate particles to very high speeds, about 6.2 kilometers per second at maximum. And here are some of our material degradation test facilities. Atomic oxygen in particular, there are only a few facilities, there are some in Europe and France, I believe, that are very good, but there are very few facilities that stimulate atomic oxygen exposure. Oxygen is a diatomic molecule. It's naturally found in pairs at Earth's surface, so keeping it separated, single O, is a challenge, and especially doing experiments with that. So this is a good facility. We also do UV exposure, and we have numerous electron guns to simulate high energy electron impacts in orbit. So that being said, what we started to do, starting in 2009, 2010, was to take what we had learned about space research and about solar array testing and put it together for satellite projects, in particular nanosatellites. So I'll come back to those two slides. So in 2010, we began to buy equipment. We got some research funding from the Japanese government and from local industry to begin purchasing equipment. We spent about $2 million US on the equipment. The facility cost was more than that. To obtain a facility that could test a nanosatellite up to 50 centimeters in dimension, X, Y, or Z, and 50 kilograms in mass. So it's a small satellite compared to large satellites that are developed by industry, hundreds of millions of dollars or billions of dollars in some cases. These are very small satellites. But because the death rate of these satellites is so high, we believe that by performing at least a minimum level of testing, we can take that number and drastically reduce it. And here's an example. We do vibration testing, electromagnetic compatibility, and antenna pattern testing. This is anechoic chamber, pressure and leak, thermal vacuum, outgassing, shock. We have a clean room. The one thing we don't have that you don't see here is radiation testing. Actually, on our satellite, the one that we launched and operated, we had a radiation problem. So we underestimated the radiation effect. We work with 3 different partners in Japan for radiation testing. So that being said, how can we, we're doing this at our university. We want to make an impact on the community. And what we did, or what I should say my colleague Professor Cho did for ESD testing, he used the ISO standardization process to streamline the protocol for certifying solar array panels for space operation. Prior to this, there were some very expensive, very highly publicized satellite failures that led to very ugly lawsuits and accusations. So finally, in 2011, this was passed, and it's very useful for the entire space community for solar array performance and testing on the ground and in space. Now we're trying to do the same thing for nanosatellite testing. So not just solar arrays, but the whole package for small satellites only. This already exists for large satellites, but it's very expensive and very time consuming. So for this project, we're trying to do 2 things. Allow fast delivery and low cost. So it's a little bit unique, and we've made a lot of progress. The initial funding runs out in March, but we've applied for more, and we think we could get this standard passed in maybe another 12 months. It's about 80 or 90% complete. So here's just a quick look. Maybe some of you are familiar with these satellites, maybe not. Mostly small satellites that have been tested since 2012 in our center. Yes?
I have a question. For example, so what are your plans in terms of, let's say, for example, a company or a space agency, they want to test their satellites, the nanosatellites.
Yes.
So they go to you, and then is there an agreement that
Yes, there is. First, I should say the primary target for this standard is industry. For university satellites, it's not that bad if it fails. It's still a great learning experience, and there's less at stake. So of course universities can use this standard and it's useful, but it's not a priority. Our priority is industry. So in that case, there are 2 or 3 things that have to happen. For a domestic company in Japan, it's pretty easy. They contact us. We have a standard contract that we start with. It's 4 or 5 pages. They fill it out and send it back to us. For a foreign institution, we have to first have some memorandum of understanding between our institution. Then we have to do 2 more things. We have to sign non-disclosure agreements and do export control to actually send the product to Japan and back. For most countries, that's not a big issue. There are some exceptions, of course, Iran, North Korea, places like that we can't really work with. But generally speaking, the paperwork can be done in 4 or 5, 6 months at most. So, and there's a fee associated, but we try to keep it low. So,
do you know how much?
It really depends on the testing. So we're not for profit. We're not trying to profit by doing this, but the manpower is the most crucial aspect. So This is just an estimate. It can vary a lot depending on the satellite and what wants to be done, but I would say $300 or $400 per day on average. But it could vary a lot. It could be as high as 1,000 depending on what is required. So case by case basis. Just to recap what we're doing in our laboratory, we have 4 research themes, and we are trying to put together the research and the actual satellite technology in orbit. And what we have that is really useful, we understand the space environment, and for satellites to consistently be successful, it's very necessary to adequately test the technology. And also we've been working on this, we're still working on this, we have lots of partnerships both domestically and internationally. So hopefully we can add some Mexican partnerships.